So we're going to move on to actually evaluating these integrals. So we know how to approximate them. We know what the actual value is by evaluating that limit. So what we're going to do is figure out how to evaluate the entire integral. So before we start actually doing a problem, we need to talk about a few things. And we've done this before in the previous section, but what we're going to do is you need to know some of the most basic summations. And so that's what we're looking at here, is three of the more basic solutions, or more basic summations. So we talked about this before. If you add up I n times, so what this is adding up is 1 plus 2 plus 3, and it keeps on going up to n. That's actually equal to n times n plus 1 over 2. So for example, if I were trying to add up from I equals 1 to 5 of I, this is adding up 1 plus 2 plus 3 plus 4 plus 5, and I could for sure type that in, or I could just use this equation that says that it's 5 times 6 over 2. So 5 times 6 is 30, divided by 2, that would give me 15. Next thing is if you're adding up I squared. So this is where you're adding up 1 squared plus 2 squared plus 3 squared all the way up to n squared. Then there's another nice formula. It's n times n plus 1 times 2n plus 1 divided by 6. So for example, let's say I was going from I equals 1 to 4 of I squared. So this is doing 1 squared plus 2 squared plus 3 squared plus 4 squared, which I could do, right? I could square all those and add them up, or I can use the formula. And the formula says it's n, so here my n is 4, times n plus 1, which is 5, times 2n plus 1, which I believe is 9, divided by 6. So let's see here. I believe that is going to be 15 again. Nope, that's not right. So I'm going to have to do this out in my head. So the 2 and the 3 go away, so I'm left with 30. That seems better. And for my last one, we don't use this one as much. This first and second one, for sure, so equations 5 and 6, but the last one is important, we don't use it as much. But this is adding up 1 cubed plus 2 cubed plus 3 cubed, etc. And it's just n times n plus 1 over 2 squared. So it's actually the first one squared, which is kind of interesting, which means that if we were adding up from I equals 1 to 5 of I cubed, which is 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, it's actually equal to n times n plus 1 over 2 squared, so 15 squared, whatever that is, I think 225. A couple other ones. If I'm adding up a constant n times, then it would just be n times that constant. So for example, let's say I was adding up from I equals 1 to 4 the number 6. This says I should add up the number 6 every time, and from I equals 1 to 4. So this is 6 plus 6 plus 6 plus 6, which is just 4 times 6. So if you have a constant, all you do is you multiply the n times that constant. Next thing is that if you have a multiple on the inside of a summation, you can bring it outside. Really, this is just factoring. So this would be something like if I was doing from I equals 1 to, let's say, 4 of 3x. I don't know, 3x to the I, something like that. I can bring that 3 out. That's what this rule says. The next one is that you can break up summations. So if I have a sum inside of a summation, you can break it up into 2. So if I had something like from I equals 1 to 5 of, let's say, I plus I squared, I could break this up to be the summation from 1 to 5 of I plus the summation from 1 to 5 of I squared. And the same thing holds for subtraction. That's the second part. So, if I just make this a plus or minus and this a plus or minus, that's putting 10 and 11 together. So these are just more rules that we're going to use when we go to actually evaluate these integrals. Now, if you go back to calculus, what we did, if you remember, is you didn't learn the rules in the beginning. You learned the limit definition of a derivative. And you had to use that whole limit as h approaches 0, f of x plus h minus f of x over h. That's what we're doing right now. So we don't have the rules yet to be able to evaluate integrals. We're going to use the limit definition. So here's the problem that we're going to do. We're going to evaluate the Riemann sum for x squared minus 6x, taking sample points to be the right endpoints. We're going to go from 0 to 3, and we're using n equals 6. So let's talk about what that means here. So the a equals 0 to b equals 3. That means that our interval on the x-axis is 0 to 3. N is the number of rectangles that we're going to use. So we're going to be dividing this into 6 rectangles. And then we're going to be using the right endpoints to evaluate the Riemann sum. Alright, so let me remind you what that equation looks like, or you can draw the picture, it doesn't matter. But the equation said that you're going to go from I equals 1 to n, our n here is 6, and it's going to be f of x sub I, we're going to need to figure out those x sub i's, times delta x. So that's what we're trying to figure out. So it was the height of the rectangle, that's your function value, times the width of the rectangle, that's your delta x, and you're going to add those up. You're going to add up 6 different rectangles. So that's what we're doing here. First thing we're going to figure out is what is delta x. Well, because I'm breaking this interval into 6 pieces, it looks like the width of each rectangle is going to be 1/2. So that was b minus a over n, so 1/2. So it looks like I'm going to have a 0.5, a 1, a 1.5, a 2, and a 2.5. So there I've broken my interval up. The width of each one of those is 1/2. Next, we have to figure out what are our xi's. So which xi's are we going to be plugging into this formula? Because we are doing the right Riemann sum, then it's going to be the right value. So here's my x1, here's my x2, here's my x3, here's my x4, here's my x5, and there's my x6. And now once you have all that, we're just plugging it into the formula from there. So here was that formula again. And like I said, our xi's were 0.5, 1, 1.52, 2.5, and 3. So you're going to plug all of those into your function. Let me remind you, your function was x cubed minus 6x. So this f of 0.5, that's 0.5 cubed minus 6 times 0.5. And you get the negative 2.875. For f of 1, that was 1 cubed minus 6 times 1. So that's where this negative 5 came from. And we would keep going. All of them are being multiplied by delta x, so we pulled that out front. That's where that 1/2 came from. And so we got negative 3.9375. So that is our right Riemann sum using n equals 6. So one thing to kind of note about that, it's not that great of an approximation. I mean, if you look at this picture, it's just 6 rectangles, and we're really trying to evaluate a curve. But what I do want to show you is that if you went back to this last slide, do you see how some of these functions value were negative? So that means that we were taking away area, which is good because it was below the x-axis. So these 4 rectangles, those were all negative because they were below the x-axis. So now we're going to figure out the exact solution. So we are going to figure out the sum from 0 to 3 of x cubed minus 6x dx. That's what we're trying to figure out here. And I'll remind you, from the limit definition, this is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of xi times delta x. So the process that we go through pretty much every single time is the first thing is you're going to figure out what is delta x. Right, what is the change in x, and go from there. Next, figure out what is xi. Once you figure out those two things, I'll plug it back into my formula and I'll do a bunch of algebra. But that's going to be the hardest part, is figuring out those two things and then doing the algebra portion. So let's first talk about delta x. So delta x is b minus a over n. My b is 3. My a is 0. 3 minus 0 is 3, so 3 over n. So there is my delta x. So when I go to figure out this problem, it's going to be the limit as n approaches infinity from I equals 1 to n, f of xi times 3 over n. So far so good. Now let's figure out x sub I. Well, if you think about breaking this interval up, so here was 3, here was 0. I know that the change in x is 3 over n, which means that every time I move to the next subpoint, so the next endpoint of my subintervals, I'm adding 3 over n. So my first one would be 0 plus 3 over n, which is just 3 over n. So that would be my first, that's my x1. My next one, I would add 3 over n again. So that would be 6 over n, which I'm actually going to write this as 3 times 2 over n. That's your x2. For my next one, I would add 3 over n again, which will give me 9 over n, but I'm going to write it as 3 times 3 over n. That's your x3. And do you see some sort of pattern happening here? Right, if I'm trying to figure out a formula for xi, I know that x1 was 3 over n. I know that x2 was 6 over n. I know that x3 was 9 over n. I need a generic formula for x sub I. Well, I think the pattern that we're seeing here, it's whatever this subscript is times 3 divided by n. So 3i over n. So that's going to be my x sub I. So the x sub I is coming from what is the general formula for your x's, those right endpoints. So we'll plug this in, which means we need to figure out this. Okay? So let's do that. First thing, let me remind you what we had before. So we had the limit as n approaches infinity, I equals 1 to n, f of x sub I, and I'm not going to draw an x sub I. It was 3i over n times 3 over n. So let me start with this. What is f of 3i over n? Well, my function for f was x cubed minus 6x. So if I'm plugging in 3i over n, that means that I'm going to have 3i over n cubed minus 6 times 3i over n. So all I did was I plugged in 3i over n for x into my equation for f. So that's where that came from. And then if you're looking at the first line in black here, the only difference is we pulled this 3 over n to the front, which we are allowed to do. You're allowed to pull out anything that's being multiplied as long as it doesn't have an I in it. So that's where we are on this first line. From there, we're going to cube everything for the first term. So 3 cubed is 27, n cubed is n cubed, I cubed is I cubed. And then also multiply the 6 and the 3 for the second term. And that's where we are from here. Now, like I said, you're allowed to pull out anything that doesn't have an I in it. Sorry. Yeah. So like on this second one, I can pull out 18 over n. We're allowed to pull that out. On this first one, I can pull out 27 over n cubed. So anything that doesn't have an I and is being multiplied, pull that out. So that's what we did. So now I have 81 over n to the fourth times I cubed minus 54 over n squared times summation of I. So that's what we did from this step to this step, is we pulled out everything that wasn't an I to the front of the summations. We also split it up to be 2 summations, and we're subtracting them. From there, what did we do? Well, if you remember on the very first set of properties of summations, I know that the sum of I cubed was n times n plus 1 over 2 squared. So I replaced that here. I also know that the sum of I is n times n plus 1 over 2. So I've replaced that here. And now what you see is we've gotten rid of the summations, and that's kind of the goal, right? You want to get all these summations down to something that you know, and then replace the summations with something else. So that's where we are from there. Once we get rid of those summations, now comes the time where I actually evaluate the limit. So here we are. I have 81 over 4 times 1 plus 1 over n squared minus 27 times 1 over 1 plus n. And I'm evaluating this as n approaches infinity. And maybe it's confusing where that last part came from. I'll come back and do this a second way in just a second. But as n approaches infinity, what happens? This term goes to 0, meaning 1 divided by a giant number is 0. This number goes to 0. This term goes to 0. So I'm left with 81 over 4 minus 27, which is negative 6.75. Now, if that was confusing, another thing that we could do is, if you think about this, the only terms that really matter are the largest powers of n. So if I go through this and really only look at the highest powers of n, let me see what happens. So I have 81 over n to the 4th. For this term, what is my highest power of n? Well, I'm going to get an n squared from the n times n, but then I'm also going to be squaring that, so it looks like n to the 4th. For my second term, I get 54 over n squared. I have that 2 on the bottom. We're going to keep that. The highest power of n, if I were to go ahead and multiply that, would be n squared. So I got n squared over 2. 81 over n to the 4th times n to the 4th is 81. These n squareds cancel, so I get 54 over 2, which is exactly the same answer that we got before. So 81 minus, what was it, 54 over 2. So we had the same answer. Negative 6.75. So what does that mean for us? That means that the actual area between the x-axis and the curve, keeping in mind that the area under the curve is negative, the area above the curve is positive, is exactly negative 6.75. So that's what we can conclude from all of this. So the integral from 0 to 3 of x cubed minus 6x dx is negative 6.75. Just to give you an illustration of kind of what's happening here, we have, if you had 40 different intervals, so instead of the 6 that we did before and you actually computed the Riemann integral for 40, you get negative 6.4. Very good approximation. Not exact, but very good approximation. And then you can see here a table for n equals 40, n equals 100, and remember, the bigger the n is, the better the approximation. And so you can see these are going towards that negative 6.75, which is the exact answer.